predicting whether a system is at equilibrium and determining its equilibrium composition. So two separate problems. That's pretty much what we're going to work on today. Two different problems. But what's the big deal here? Well, I guess if you want to breathe or walk or lift a pencil, think, this has to go on inside you, otherwise you're not going to have the energy. What's the G word? Glycolysis, right? There's a lot of equilibrium going on in there. Look at all that. So you could say, in a sense, your life depends on this, right? So with the symbol for the equilibrium constant being Kc, Gabby, what does the C stand for again? What's that? Oh, not constant. It is a constant, that's true. Although it sometimes changes. But the C doesn't stand for constant. It stands for concentration. The C stands for concentration. So we haven't got this far to realize that there's other equilibrium constants, like a thermodynamic equilibrium constant. But the reason why they're sticklers with the C is that everything has to be in terms of concentration, whether it's a gas. Just don't put in solids and liquids, of course, but something could be a gas, and you still have to put it in its concentration. There's only one way to change the number of an equilibrium constant. Like let's say an equilibrium constant is 12. There's only one way to change that number. You have to change the temperature. Very good. Because good problems, they actually give you the temperature. Because if you change the temperature, you're going to change the equilibrium constant. But it's kind of more information than you need to do the problem. But little review here. Sabina, here's a reaction. And they told us the equilibrium concentrations are right here. They want to know what a value for Kc is. Is this an ice problem? It looks like it, doesn't it? What's Kc again? Products over reactants. And everything has to be at its equilibrium concentrations. Well, that's what they gave us. All right, so I guess you kind of got to be careful, right? Because not everything's going to be an ice problem, but so this isn't. So go ahead and try it. Calculate the concentration of products over reactants. All right. Like for example, let's make sure everyone's on the same page here. Vivian, what number would be up on top? What number would be up on top? Yeah, what number would you put up here? .5. Is it just 2.5 or is it raised to a power? Raised to the 2. All right. And then go ahead and write the bottom part and see what you get for Kc. So on your calculator, I would figure out how to use the x to the y button. Let me show you what I mean. You may have got an answer already. But I'm going to use the x squared button to get my 2.5 squared. Right? 2.5. Push the x squared button. And then hit divide. Push 4. Hit the x squared button again. Hit divide. 2.5. And I want to raise it to the third power. What button do I push to raise stuff to a power? X to the y. Good. So push the x to the y, then a 3, hit equals, and I got 0.025. Okay. Make sure you can do that. We're good? So that's our answer. Let's put that answer down. If you scroll down to the next problem, where way down here, it goes here. Right? Where we found Kc in the last example to be 0.025. So let's put it down there. Okay. So I believe, yep, this is where we're at right now. There's two problems, two types of problems. The first type of problem you're going to see in the homework is how can you predict if a reaction is at equilibrium? And if it's not at equilibrium, it has to shift either towards reactants or has to shift towards products to get to equilibrium. Okay? So the question is going to be, are you at equilibrium? If not, which direction is the equilibrium going to shift? So they're going to give you all these concentrations and things, and the solution is to calculate QC. Okay, fine. Calculate QC. Well, what the heck? Now, they call QC a reaction quotient. Jerixa, how do you write the expression for a reaction quotient? What is it? Right? You're supposed to be able to calculate this thing. What do you write for it? Right? Yeah, well, you're close. For example, this one is coming up. And they're going to say, is it at equilibrium? And they give you all these concentrations. Pretty much all you do is write the Kc expression, products over reactants, but we're not supposed to call it Kc because we don't know if we're at equilibrium. So you erase the K and write a Q. That's all it is. It's just a trial equilibrium constant. So you calculate the concentration of products over reactants. So you substitute in, you're going to substitute in all these numbers. You don't know if you're at equilibrium or not. You're going to substitute them all in, okay? And you're going to calculate a QC. Then you're going to compare it to a Kc, right? They have to give you this stuff. They have to give you the concentrations to plug in. They have to give you what the true equilibrium constant is, and then you compare your reaction quotient, or QC, to Kc. And you have three possibilities, right? Either it's going to be too big, what you calculated, or it's going to be too small, or it's going to be exactly the same as Kc. There's only three possibilities. So let's start at the top one. Danny, you calculate the QC, concentrations of products over reactants, and you get a number that's too big. Well, that means that there's too much product. Good, because these equilibrium constant expressions are always products over reactants. So if your number's too big, you have too much product. Well, that means it has to shift towards the, I don't know, am I right or left? I don't know. But reactants, right? It has to shift towards reactants. So it has to be back this way, right? So it has to shift towards reactants. If QC is too small, now you have too much reactant. Right? You have too small of a number. Right? This number is way too big. So you have too much reactant. Well, now it has to shift towards products, which is in that direction.
Does exothermic and endothermic still come into play?
Nowhere. But what if you hit the third possibility, Diana? QC is the same as Kc. Then what? Yeah, then you're at equilibrium. Then you're at equilibrium. Okay. So let's try it. We know what the equilibrium constant is. Kc is 0.025. Here's a bunch of concentrations for everything. Determine if you're at equilibrium or not. Try it. Calculate a QC. steal an answer here. Crystal got .038. Oh, a lot of people did. 0.038. Erica got it too. Right? Okay. Somewhere around there. Depends on how many digits you're carrying and stuff, but it should be somewhere around there. Are you at equilibrium? Most definitely not. Which direction will the reaction shift? To the reactants. Yeah, because it's too big. You have too much product. So you can do this, or say toward reactant. Either way works. Okay. So that's the first type of problem. Not too bad. They give you a Kc, give you a bunch of concentrations, and you determine whether you're at equilibrium or not. The second type of problem. You may not like this one as much. Okay. When you're given a Kc and their reaction, and they just want to know what's the equilibrium composition, right? When you finally reach equilibrium, what are the concentrations of everything? Okay. Now that's different than what we did in the past. Before they said, yeah, they want to know the concentrations of everything at equilibrium, but they gave you one of the answers. Here they're not giving you anything. They're just giving you Kc, the reaction. Okay, you figure it all out. The answer, the solution. Make a blank table, then do blank. Does anybody know what I'm driving at? Well, we're going to do ice. What kind of table are we going to make? Not a mole table, but a concentration table. We have to, it has to be concentration. It has to be. It has to be a concentration table. Mole tables will not work. You have to make concentration tables. Okay? And you'll see why. Let's work this one out. So they said that you have a 1 liter vessel. You have 3 moles of chlorine, 5 moles of bromine. And they said Kc is 50. What are the final equilibrium concentrations? Concentrations of everything. Okay. So we need to make a concentration table and then do ice. So let's go ahead and try that. Do a little ICE here. But I can't put in moles, I have to put in molarity. But yeah, the volume is 1, so you got to be careful though, right? Because this is just trying to make things easy. But you know, the next problems, the volume isn't going to be 1, so you're going to have to do some dividing. But this is going to be a 3. Bromine will be 5. And monobromine monochloride is there anything there? Dash, nothing. Okay. Let's see if Alejandro's not here. Tegan, see if she remembers how to do the change row. Negative x plus 2x. Perfect. Okay. Now the E row, or equilibrium, that's where all of our answers are, Allison. What is that going to look like? We just add them up. You have initial, you have a change, so, well, a negative x plus 3, or 3 minus x. Just add them up. Right? And 5 minus x. And just 2x. Yeah, 2x plus nothing is 2x. Okay. Those are all of our answers. We just have to figure out what x is. Now, Jasmine, in the past, they gave us one of these. And then we just said, oh, 2x is equal to 7 or whatever. And then we solved for x and we figured them all out. Now they don't tell us anything. So what could you do now? We got to use that 50 for something. Good. But let's write the expression so we don't screw up. I hate going through all this work and then screwing up. So this saves me some time. Kc, let's write the expression for it. Yeah, product of reactants. So I'll have what on top?
BRCL.
BRCl. Perfect, squared. It's just, I don't know, man. Just people don't forget to write the squared if they write the BRCl. They just don't. Then on the bottom, just chlorine and bromine. So it's a healthy thing to do because you're going to see this is a lot of work, this problem is. Okay, now we substitute everything in. Kc is 50. Now what is my BRCl? It is 2x. But I got to square it. Good. Then on the bottom, I'll have 3 minus x and 5 minus x. Is this starting to look familiar? All right. Okay. So let's let you struggle with this, and then we'll go through it, right? What's the first thing you probably do? Yeah, you can distribute first, or move this up here first, and then distribute, right? So give it a shot. And if you're not sure, just ask. I'll be glad to help you out with this.
Could you like simplify it?
Oh yeah, you can divide through by 46 if you want.
And then we use the simplified that we've
Yeah,
okay?
yeah, you could divide everything through by 46.
Okay.
But it just end up with decimals and things. So, and since you have a calculator, you're really not saving any time. In fact, you're actually kind of playing with fire. Because if you divide through by 46, you have to do everything correctly and write it all down correctly. It's just one additional step. So to me, it's safer just to use this.
Once we have ABC, do we?
Oh, we need that formula, don't we? Negative b plus or minus the square root. I give you this stuff. Yeah, you don't need to memorize this. And it needs to be in the form ax squared plus bx plus c equals 0. Yeah, thank you. I forgot to give that to you. So I don't know if yours match mine, but I got 46 for A, negative 400 for B, and positive 750 for C. Okay.
How did you get 4x squared?
Because they had 2x times 2x.
I see. How did you get 46?
Okay, so what I did, I had two choices. I can bring all this stuff on this side or bring this guy over here. So I just add negative 4x squared to both sides. So 50 and a negative 4 would be 46.
Two x, right? So 2x times 2x.
Yeah, 2x times 2x.
I was like,
did I do?
You put force.
Negative b plus or minus.
So you put instead of b, you put a.
Oh my goodness. Oh my goodness. Negative b. That should be positive 400. Plus or minus 400 squared. Oh, it's negative b though. Doesn't matter. Negative sign goes away when you square it. Minus 4ac divided by 2a. All right, that looks better. Thank you. Whoa. Okay, here's my two answers. I don't know if hopefully yours are the same. I got a 2.74 or 5.96. All right. Did you get those, Tegan? Okay. See if you can figure out one of those has to be wrong. You can't have two possible answers here. One of those is wrong. Yeah, go plug them in to your ice table, and you're going to see one of them doesn't make sense. One of these is not going to make sense.
Well, it can't be negative, right?
It can't be negative. That's it.
So it has to be 2.7.
Yes, perfect. Crystal, you're exactly right. It can't be negative. So it has to be the 2.74. Yep.
If you multiply the two negatives together, that's a positive.
No. This is your answer for chlorine. It has to be 3 minus x. So you can't have a negative answer. What is that, 0.26? What's the other one? Bromine, 5 minus x. What's the last one? BRCl. What was that, 5.48 or something? There's all our answers. Right? Make sure you put big M's on your final answers, otherwise you'll lose a point. The units. Okay? So if you got this, go on to the next one. And be careful, volume is not 1 liter on the next one. If you didn't get this, let me help you out. Oh, the next one is, oh, sorry, the next one is a conceptual question. So you ready to go on to the conceptual question? Nothing to calculate on 57. Yep, Crystal?
Why is BRCL 1.5? I mean 5.4.
It has to be 2x. And I did that in my head, so that might be wrong. What's 2 times 2.74?
5.48.
Oh, it is 5.48. Good.
Oh, I was solving
Yeah, no, it has to be 2x from the table.
Just plug it in. for
Yep.
instance.
Good. Perfect. Okay, any other questions on this one? So the idea is make a concentration table, do ice, and then set up your Kc expression. Okay. 57 is nothing to calculate. It's just something that we need to get used to talking about. Solely on the basis of the value of the equilibrium constant, decide whether or not you expect nearly complete reaction at equilibrium. And what this means is that you have all product. No reactant. I mean, there's hardly, it's very little reactant. So if that's the case, what type of K would that be? Huge. Has to be big. So you look at this, is this big?
No.
No. So you'd say no. Okay. So, because it's, look at this, 10 to the negative 31. I mean, this reaction hardly even started. You can get hardly any product out of this at all. Okay. Try 70 and realize that the volume is not 1 liter, right? It's actually 4. So try setting up 70. Thereafter, the equilibrium composition. And they give you the initial amounts, so it's definitely setting up a concentration table. Then do ice. Bless you.
Thank you.
That's how I set up my ice table. Hopefully you got something similar. Oh yeah, yeah. I got to divide by the volume. These guys have to be the concentration table. It has to be moles divided by liters. It's going to be 0.1. For my A, I got 49, B negative 10.8, and C 0.49. Oh, good. Okay. So I don't know, maybe with rounding, you may have got something a little different, but hopefully you got these two for your X. And which one turns out to be wrong? 0.156 is too big, yeah, because those two X, 0.1 minus X, yeah, that's going to be negative answers. So pick the 0.064, and then PCl3 and Cl2. Right, 0.036 or so. And the last one was just X. PCl5 is just X. And X is 0.064. Okay. So they're work, but they're doable. Not forever. Nah. Just take your time on them, otherwise they can get frustrating, right? So come by, especially tomorrow. I'm in lab all day. Just come by. I'll be glad to help you out. Have a good day.